computational biology, statistics, modeling, and bioinformatics. As a technical staff member, he exemplifies the impact of dedication and research. Mr. Bindawa has developed groundbreaking methodologies, including Kabirian-based optinalysis, statistical mirroring, spacing, SM-based ordinalysis, and expositometrics, which propel advancements in biological data analysis, entomology, medicinal plant conservation, and integral pest management. Additionally, he is skilled as a Python programmer, which innovates statistical implementation. His research has been featured in prominent high-impact journals. So we welcome you to make your presentation. Please let's put our hands together for Mr. Kabir Bindawa.
On a statistical.
Proceed. Good morning, everyone. In the beginning, I would like to express my appreciation and gratitude to Department of Botany, ABU's area, the organizers, especially the HOD, for this opportunity. I will be with you this morning to present my paper, which title Robust Estimators, how they can be used to improve research and data analysis in botany. The essence of this presentation is just to remind us and update us on some existing statistical tools that we have been using in our daily research. And I will be introducing you to new statistical framework, which is statistical mirroring, how it tries to solve some unsolved problems in statistical analysis. From the slide, can I do it? Okay, sharing. Please can someone go? The slide. Just one second. Okay. Thank you. Let me start by asking us a very simple question. Do we know that about 40% of our plant species are facing extinctions due to environmental changes and climate changes, whatever? But yet, this analysis of this botanical data still relies on conventional statistics. This reliance on these conventional statistics has led to so many statistical conclusions that we have to improve their accuracy and their precision. We use these statistics to infer meaning from the information we derive from our data, and most of these classical statistics still do not capture the nuance meaning of the data. Now, accurate quantitative measurement is critical in botany, but yet many of these traditional methods have some irregularities and struggle with some bias that are as a result of the estimator that has been used. That is why this research is crucial, where we'll be discussing the aspect of robust, efficient estimators, how they can be used to produce a more reliable insight from the data. In this seminar, I will be discussing some of these statistics, some of these estimators, and how they have been used to improve data analysis. Okay, let me start. The slide is not showing. Okay. Here I'm presenting you the outline of the presentation. We'll begin with the quantitative measurement. We'll go through how it looks in botany. We'll describe some of these statistical terminologies. We'll go into the essential features of quantitative data. We'll now discuss the guiding principle for choosing a statistical estimator. We'll discuss some scope and limitation of these statistical tools. We'll examine on sub-statistical problem of dispersion measurement. I'll be introducing you the framework of statistical mirroring and some of the implementations. Finally, we'll conclude and give you some takeaways. Okay. We know in botany, we take research involve data collection, and we need to infer meaning from our collected data. And the implication here, the quantitative measurement needs robust and efficient estimators to provide a more reliable conclusions and generalization from your data. Okay, we'll be starting with what we mean by quantitative measurements. A quantitative measurement, from what it has been written there, is just assigning numerical value to your object or to your attributes. When you assign numerical values to your attributes, you need to make comparison, you study the trends, and that helps you to make decisions and draw a reliable conclusions. And one key thing in quantitative measurement, you have to make sure your instrument of data collection is precise, reliable, and valid. That gives you a more reliable quantitative data. Then the next thing, why quantitative measurement in botany? You are interested in making a systematic conclusion that helps you to draw a meaningful conclusion. You may be interested in studying the pattern and the relationship in the trends of your data. And finally, you make conclusions that support conservation in medicine, ecology, and other disciplines of botany. Now, what quantitative measurements entails in botany? We can't ignore the role of empirical or ecological indices. These empirical or ecological indices, they are not a statistical functions, but they may or may not have a statistical support. They are used to analyze data and drive a meaningful conclusion. If you look, we have some examples, which are some of the very key metrics we have been using. These are just some of them. The use value, habits index, root ratio, and others. These are what we call ecological indices. They are the very essential estimators in analyzing botanical data. Next, why statistical estimators? Statistical estimators, those ones, they have a strong statistical support. Why do we analyze our data statistically? We intend to make summarization to summarize your data. That is to describe your data, or you are interested in inferring meaning from the data. You make inferential judgments, or you may be intended to make predictions from your data, or you intend to make comparisons. So these are the key things why statistics is essential in botany. I think for us to understand the key concept of statistical mirroring, which is the framework we are trying to introduce to you in this presentation, we need to understand some of this terminology. We all know them, but we need to refresh our mind. We need to just glance through them. The first one, what do you mean by estimator? I will be mentioning estimator. What do you mean by estimator? So estimator is just nothing but functions or rule or any formula that you use to analyze your data. This is what is called estimator. Mean, median, mode, ANOVA, MANOVA, chi-square, t-test, all these are estimators. Then we also go to the estimates. When we say an estimate is the result, the value you generate from the estimator. When you look at this, we have numbers. When we calculate the mean, this 7.2 is the estimate. It's the estimate of the estimator. Then we also have another term which is unbiased, unbiasedness. What do we mean by unbiasedness? Unbiased is when the expected outcome of your analysis is close or equal to the true parameter of interest, the parameter you want to estimate. When you look at the mean, a sample mean is an unbiased estimator of a population mean. So a sample mean is a true estimator of your population mean. So in this case, a mean is an unbiased estimator of a population mean. So also have another statistical term, efficiency or precision. What do we mean by precision? A precision is when the expected outcomes are very close to each other, having very small variance. When there is small dispersion, small spread, they cluster themselves around the true population estimate. So let's say we have estimators, theta 1 and theta 2. So if theta 1 has 2.5 variance, theta 2 1.5, we can just conclude that theta 2 is more precise over estimator, this theta 1 estimator. So this is having a small variance of your calculated estimate is what signifies efficiency or precision. Also have robustness. This issue when we deal with outliers or extreme values. You have your data, the presence of outliers or extreme values may lead to bias. So when we say robustness, how does the estimator resist the influence of external or extraneous values or outliers? So if an estimator can resist without changing the data, without deviating much from the expected true value, that regards an estimator to be robust. When you look at this, we calculated the mean from the first data. which is 2.5. When you plug this 50, which is an outlier, it should be 5. Maybe while typing, you type 50. So that has become an outlier. So if you take mean, because it's sensitive to outlier, it's no longer giving you 2.5, but rather 10. But median, which is a robust estimator in this regard, has returned the expected, which is 2. It doesn't change with extraneous values for outliers. We have consistency. A consistency is when you calculate your estimate with increasing sample size, the expected or your calculated estimate is close to the true population parameter. As you increase the sample size, it tends moving close to the expected value. So that qualify an estimate to be what? To be consistent. Sufficiency. A sufficiency is a situation where an estimator can handle or can capture the necessary information of your data. We can make comparison from mean and median. Mean, you have to incorporate all the data, but median is just the pips percentile, that is the center. It regards other data. It's just the center. So in this case, mean is more sufficient than median. So this is also very important. We also have what is called scale invariance. What do we mean by scale invariance? Is when you have your data, you keep multiplying that data by any number from natural number. Any number you multiply, the result doesn't change. For instance, you have 1, 0, 1, 2, 3, 5. If you multiply it by 10, having 10, 20, 30, still it doesn't change. So if an estimator, that means that estimator is what? Is scale invariant. It doesn't change with changing the scale. Whether you use centimeter, kilometer, millimeter, micrometer, the result wouldn't change. They also have location shift. A location shift is when you shift your data point and the result doesn't change. You have 0, 1, 2, 3 to 5. If you shift by 5, you have 5, 6, 7, 10. So a scale, a location shift invariance, it doesn't change even if you shift the location of your data, despite having same variability, that is dispersion around the center. Then we have permutation invariance. Permutation invariance is dealing with the pattern of your data, the order in which the data, if you change, there are some estimator, when you change the pattern, the order of your data, it keeps changing, it keeps giving you different results. But a permutation invariant estimator is even if you change the order of your data, it doesn't change the results. As you see, we have this, when we change the order, it still remain. Then we'll be taking to the next session, which is understanding features of quantitative data in research. We have been undertaking research. We need to know what are the key features of your data. These key features can range from intrinsic to external transformation. Why are these features? Why do you need to understand the key features of your data? Because they are very important when it comes to improving the model, your model, improving efficiency of your estimator, and drawing a reliable and valid conclusion. Now, let's start with the intrinsic features. These intrinsic features, you have to understand, or you have to know the scale of your measurement. Because we are talking of quantitative measurements, so any quantitative measurement is any measurement above interval ratio. That is, interval and ratio is above ordinal. So specifically the interval and ratio scale, you have to know your data. Is it at interval or on ratio scale? Why is this significant? It guides you on choosing the appropriate estimator for your data. You also have to know, understand the outliers. You need to understand whether your data has outliers or not. You already have discussed what these outliers. Maybe you have this number. It is just going 53576. They are very close to each other, but 100 having 100 is going outside the. It's not that big. It's just an outlier. So you also have to understand the sample size. What is the sample size of your data? Knowing the sample size of your data will guide you on which estimators to, because some estimators are very sensitive to sample size. And we know sample size is very important key when it comes to making a valid and reliable conclusion. Having small sample size may be biased than having a large sample size. So also have some external transformations. Some external transformation include the scaling transformation. Maybe if you have collected your data, whether through research or you collected a secondary data, so you have to know what is the scale of your data. Then you also need to know whether the data has been shifted, whether it has been transformed through location shift. Or you also have to understand the permutation of your data. Has it been transformed? Is it in its true recorded pattern, or the pattern has changed? You also need to understand, to know about the linear transformations, the non-linear transformation, which are nothing but the log transformation, the reciprocal relationship, and others. You also need to understand the standardization of your data. Is your data in standardized form or in a normalized form? So I think let's just, from the external, you also need to understand whether your data, how to deal with missing data. So you can correct a missing data through these techniques by list-wide deletion, or through mean-median imputation, or you can use some predictive imputations to recover your missing data. So you also have to understand the concept of aggregation or discretization. The aggregation and discretization, that reduces the complexity of your data. You have very huge data, so you need to aggregate it or to discretize your data so that you have a very small groups of meaningful relationship. You can achieve this through binding, through averaging. Now, what guide you to choose a suitable statistical estimator? As I said, you have to understand some critical. This is very crucial in accurate and meaningful analysis. It depends on several factors, which include the characteristics of your data, the purpose of analysis, and the limitation of the estimator you wish or you choose to work with. From the characteristics of data, you need to understand the type of the data, what distribution it conforms, the sample size. That is the characteristics of the data. The purpose of the analysis. Are you intended to make summarization? Are you trying to make inference or comparison or prediction? So you have to know what is the purpose. Why doing the statistics? And you also have to know the scope and limitation of the estimator you have chosen. If I'm using mean, I have to know when mean is suitable. If I'm using median, I know why I'm using mean. So true understanding the limitation of each estimator will guide you in making a proper choice of an estimator. Now, these are some of the statistical estimators, very diverse. This is just a highlight. So our concern here in this presentation is we will discuss the limitations of central tendency and measures of dispersion in particular. So these are some of them. If you look at the mean and median, mean is not suitable when your data have an outlier or is not normally distributed. But median is that because mean is a robust outlier, that is why it's suitable when your data is not normal or contains some outliers. So these are some of the limitations. When you go for the other dispersion estimators, there are so many dispersion estimators ranging from mean based, median based, quartile based, decile based, and those with some modification that are built based on certain modifications such as visualization and trimming of the data. So in this presentation, we'll also limit ourselves to variance, standard deviation, and coefficient of variation. So I have a table here which summarizes these estimators, some of the limitations, and some of the weakness. I have highlighted some key important characteristics, the limitations of these dispersion estimators. Let me go straight to them. The applicability to both interval and ratio scale. Most of these estimators is depend whether your data is in ratio or is on interval scale. The probabilistic bounded range. Some of the estimators are not, they are not within a probability bounded range, like standard deviation. It's just dependent on the mean. So you can't make any, the outcome, the estimate is not bounded within the probability range. The invariance. One of the interesting things with these dispersion estimators, you either have to choose between a location shift invariant estimator or scale shift invariant estimator. You have to know that location shift, whether it is combined both. So we need an estimator that combines both these properties. Resistant invariance to location shift, and at the same time, the scaling. So if you see any estimator from the existing statistical tools that can combine scaling shift and location shift invariance. We also have the issue of heightened resistance outlier. So it has to resist, even if not robust, but it should be very resistant to the outlier. So these are the key limitations. So this highlighted a rate, these parameters or these characteristics are important when it comes to choice, and they're the main limitations of these dispersion estimators. So what is the challenge? The challenge here is robust efficiency. So we need a trade-off between, there is a trade-off between robustness and efficiency. So when you are choosing an estimator, you have to know that it either sacrifices efficiency for robustness or sacrifice robustness for efficiency. This trade-off between efficiency and robustness has left you with choice. You have to choose. What are you looking? Which one do you choose? Which one do you prefer? Do you prefer robustness or efficiency? So the ideal, we need to have an estimator that is robust and at the same time efficient. Then the interpretation. This is the problem lies. We have a data here, X. We transform it. I said scaling. We multiply. Go. Then when we multiply by 2, by 5, we shift the location by 2 and 5. Then we combine location shift and scaling. We multiply by 2, we shift it by 5. Here we multiply by 5, we shift by 2. So we employ different transformation. Our assumption here, a true estimator should give you the same estimate. It shouldn't change. It shouldn't, because you transform it, the estimate shouldn't have changed. So do we have any estimator that can do this? Let's check. Standard deviation. When you take the first one, red, that is the true value. So when you look at the standard deviation, it only gives you, it only equals to the true estimate at when you shift. So we can conclude that standard deviation is just what? A location shift estimator. It is only invariance to location shift. But when you change the scaling, so let's check. CV, which is coefficient of variation, is quite good. When you multiply by any number, it won't change. So can we have any estimator that combine the both two? We don't have. From the existing statistical tools, none of the estimators can give you this ideal outcome. So that is why the next challenge is the issue of comprehensive. That is what I'm trying to explain. The comprehensive transformations. It has to be comprehensive, combining both location shift and scaling. Now, that is why it matters. We are now introducing you a new statistical framework, which is a statistical mirroring, which is resilient, efficient, and complementary alternative to statistical dispersion estimators. This very interesting paper published has introduced you a statistical mirroring, which address these key limitations we are trying to explain. It has been published by Abdullah Kabir. And the inspiration from this paper derived from his text, from his post paper, which he named it Kabirian-based optionalysis. So the inspiration from this, from statistical mirroring, derived from this paper. So what is this? What this paper? What statistical mirroring? Let's dive deep into what is statistical mirroring. Is, as I said, is resilient, efficient estimator. Is just estimating how closer or how okay. 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 Thank you. Sorry. Okay. So here is the here is the app. You run it. Since you interface like this, you click on here. You go to your desktop. We save the file. It has been saved in the desktop. You search for test. Okay. You select here. Did you save it in CSV file or Excel? Click here. We save it in as Excel. So once you click, you see it go. Then you click on it. You click on Open. It says uploaded successfully. So it has uploaded. All right. Maybe you want it by this default. As main, turn the absolute. You want head to head. You now click here. Maybe let's say you want all the estimates. Then when you select your parameters, you click on compute. It has completed. Then you save. You save it. Test outcome. Then you click on save. Let's put it on desktop. You click on save. Analysis completed, results saved. It has shown you the directory of your file. Click on OK. That is all. You just go and see copy your result. So if you can switch to the Excel sheet, you will see that there you see the output. Sorry for the interruption. So there are so many glitches. I think that should be the last sharing. Desktop. To see the desktop. Yes. Test. Yeah. Yeah, that is it. That is how. Is this showing on the screen? Just cancel. Just resume. Excuse me. Let's expand. And share the slides. Is it not? The audience are not. Yeah. Okay. This is the outcome. That data we generated, we run it. This is the analysis using statistical method. But this one we have chosen it. Statistical absolute unique mirroring. This is what we did, which is recommended to be more robust, efficient, and reliable over using standard deviation. This one it computes the passion from the regardless of any information. So you can compare it. And one interesting thing is all within the probability bounded range. I can say my data deviated from this by 2%, 3%. You can make a conclusion to more very probability in sense of in terms of probability sense, rather than just standard deviation. It varies with the mean. So this is how the outcome. So just copy anyone you like, either the mean or the proximity or the deviation or the alternative of proximity. So why this value? If you take this value or this one and translate it, all arrive at same estimate. Using that y rule, it's just in y shape. So having the end, you translate now have the same outcome. And you can move. And you can come back. Just know the probability of deviation. You can turn back any of them. So from the estimate, if you know any of this estimate, predict, or you can compute back any of these estimates. So using the appropriate functions. So I think it's just easy. Very easy to use. So I think that is all. Let's share the normal presentation. We invite questions. Share normal slides. Which one is the normal slide? The share? Yeah, we share. Let's go to the last. Okay. Thank you. What is your question?
Thank you. A wonderful presentation. Please, can we run up? Any question, please?
audience and
Okay, please, if you have any question, please. Okay. Go ahead.
Thank you very much. Okay, no problem. Thank you. Can we have the questions and responses?
Dr. Said.
Statistical mirroring.
Probably I missed it. Okay. And again, if something trigger us to use it, what will end is that going to serve a kind of final answer, final result that we are going to make different with our conclusion, or we are going to use what we get to do further analysis between other statistics.
Yes. Thank you. Please. Any other question? Any other question?
Thank you for the presentation. I have some questions. How do I get in touch with the visitor? I'm going to change from one estimator to another. The second question is mirroring changes in transformation. Then the third one is what informed the choice of selecting vertically mirroring. Then I have questions like why display your results? Why display your results? That R value I don't treat is like 24. Thank you. Like 24. Thank you.
Okay, other question, please. Okay, any other question, please? Okay. Any other question, please? Okay, let him respond.
Okay. Thank you very much for the question. When we ask questions, yes, we really understand, and we really have interest. The very first question, can we use statistical mirroring in case of epidemiological events, or in case of predicting some environmental events? Actually, what statistical mirroring is trying to address, we do statistics based on the objective. Are you towards summarizing, or are you looking for an estimator? Are you looking for impression? This statistical mirroring is trying to improve a summarization of your data. You have your data, you want to make sure while summarizing your data, you always use mean plus or minus standard deviation. That standard deviation, what does it entail? If you have A treatment and B treatment, with that standard deviation, for instance, it's telling you how reliable. What confidence are you that? Because you are using the mean to say this is greater than this. So what guides you? To say yes? This is higher than this. For instance, I have a mean of 5. Other one I have a mean of 7. Definitely, I say 7 mean is greater than 5. But what if the is there? You get a standard deviation, 90% deviation from the mean. That means there are so many outliers, there are so many irregularities. So you have to be careful. It's telling you the accuracy, how reliable is that estimate, and explain about the population. So in terms of predictions, we use regression. Want to model event over time, and most of these regressions and regression models use descriptive statistics. There is a connection between descriptive statistics and inferential statistics. Inferential statistics use often from descriptive statistics. Let's say when you take an analysis of variance, you hear the word variance, stop of standard deviation. So if the estimator you use differential statistics, or you make a prediction, if it's relying on the also have relationship with the description. Are you using the mean? Rely on the mean? What is the limitation? That is why when you're using statistical tools for prediction or whatever, you have to choose between is it parametric or choosing between parametric and non-parametric. You rely on whether that estimate can resist outlier or is susceptible to outlier. And most of these statistical models are based on assumptions to satisfy this. The essence of statistical theory here, future research, not interested in modeling, whatever. You can see how can you incorporate this statistical mirroring as a descriptive estimator to improve efficiency and inferential statistics. So in future research, I'm very sure I have one paper which is trying to be a complementary alternative to ANOVA. I think, but just using the statistical mirroring again, because when we are talking of inferential, we have to use descriptive information of our data to predict or generalize or find meaning from the data. So statistical mirroring is just a step forward but improving precision, accuracy, and robustness those conventional inferential statistics, those used in predictions, those used in inferences and other analysis. So you have to know the limitation. But statistical mirroring is summarization data that is descriptive, describing. No, descriptive. When I say descriptive, it may be central tendency or the dispersion. The description here is the dispersion of your data. That is why it's trying to find how close or how distant is your data point to the center. The center can be median or not. So you just try to appreciate the dispersion of your data. Have you committed errors? That will tell you whether your mean is reliable for comparison. If you have high standard deviation, telling you one having a small dispersion, the other one has dispersion, it's telling you have to be careful. That means saying this is greater than this. You have to be because the other one has much probably outliers. So that may be why it's better. Maybe if you can reduce outlier or you normalize it, you might maybe having advantage. That helps you to improve precision so that you draw a valid and reliable that support policy and improving research in botanical. And the second question is the suitability of statistical mirroring pressure. And I think as I have just explained this. How do we know whether you find double estimate and when to switch from one estimator to the other? You only know that you have using a correct estimate based on the purpose. What is the characteristics of your data? To know whether your estimator you have chosen a correct estimate, what is the purpose of analysis? Then what is the limitations of estimate? What is your data? Has your data, your data satisfy the assumption and the requirement for that estimate? Yes. You have now selected appropriate and suitable. If not, it violates any of the assumption. It means you have to switch another estimate. So depend on the characteristics of your data, the purpose of the analysis, and the limitation of the estimator you choose to use. And I think, is it translation? He said, as I said, this element of statistical mirroring is invariant in linear transformation. Why is it applicable? We normally try to see whether a student has replicate a data. With this statistical mirroring, you can check whether someone has other person's data. Normally, how we manipulate data, you have somebody data, just add a number. Let's say you add a number to all the data points. The mean will change, even the analysis will change, but you all arrive at same conclusion, isn't it? Somebody said, you can't compare it. If you compare, the mean is the same, the dispersion is the same. Most of the statistics give you different results, but arrive at same conclusion. So this statistical mirroring, if somebody has it on, you copy it, manipulate it. Whatever manipulation you do the data, provided prove across all the data. Statistical mirroring will tell you that the dispersion is exactly the same. And I'm very sure way two researchers will do research and the dispersion will be the same. So this is how we're trying to trace if somebody has replicated or modified someone's data, because it is invariant any transformation. Transformation you make to the data, statistical mirror will tell you, will flag it as same dispersion. So forget about whether the mean is whether you use standard deviation, different result. Statistical mirroring expose this application. And is it free and open access? Yes. You can download it free. Free open source. Free. Everybody can use it. I have given you the link. Download. Free. So it's a free version. Thank you for the question.
Thank you very much, sir, for this presentation. However, I have a question before we go online, go for the online business. I have one question. Is there any pattern for arranging your data before you can do the analysis?
Okay, there is no any clear pattern.
The issue is we are life sciences communication, or experiment about data. Don't just increase data like that with reputations, so you pass away or pattern.
If you are very much familiar with standard deviation, you can calculate standard deviation same manner. You have your data, blocks. So each data point is a separate variable. Maybe I have A over different treatment. We give it a treatment. Maybe we take replicate 1, replicate 3, replicate 4. So what you do here depends. Within each replicate, can you make several measurements? If you have, you can measure how close, how distant are your distance. It just depends on the task. Just depend on the task. Do you want it in replicate wise, or do you want it in a group wise? One condition is that you must have more than two data points. If you have more than two data points, see how dispersion, what is the probability of similarity. So what you did, when you have your data, put it on Excel, run it to give you the dispersion. Same way you did it. It's just a complementary alternative standard deviation.
Thank you so much. For this. I don't know whether the online listeners have a question for you. I think we have some. If you have questions, please come. Who said you have a question? Yeah, I don't think we have a question. Thank you so much. And we do hope when we this kind of presentation, I'm sure we listen and we also enjoy it. So our next seminar is end of this month, right? March. Okay. Let's have another presentation. Thank you. Yeah. Please, can we put our hands together for him? Can we put our hands together for Thank you so much for coming, sir. Thank you too for coming. I hope you have a wonderful day. Thank you so much.
The slide is not moving. Okay. It's not going. Yes. It's not going. Okay. We will show you why statistical mirroring is highly efficient, how we compare the efficiency between the other existing statistical tools. We will see how it has succeeded in being more consistent, and we'll show you why and how it has emerged as a new statistical, a new category of estimation, which I name it scale-ups. So this is a coin term. I've just coined it as scale-ups, combining scaling and location. Scale means scale, log combines scale-ups invariance, that is invariance to both scaling and location shift. And we'll also see why or how it can work with ratio, ordinal, or interval scale, and how we can use it to make comprehensive comparison across data. Thank you, Prof. Okay. You appreciate the beauty of this finding. So each plot here, we generated about 250,000 random numbers. We analyze it, we compress it in this beautiful outlook. So when you look at standard deviation, you see it changes as we change the scaling. As we transform, it keeps changing. It looks like propeller. So this changing dimension is due to the scaling. I mean, it's not invariance to scaling. But when you shift the location, it remains the same. So when you look at our proposed estimators, you see it gives you just a uniform. So regardless of the transformation you import or you provide or you made to your data, the estimates remain the same. Now, this is coefficient of variation. This coefficient variation is complementary alternative to coefficient of variation. It changes as you change the scaling, similar to coefficient of variation. But when you look at this, the coefficient of variation is dependent. Outcome depends on the mean, whether the mean is negative or positive. So if the mean is negative, the outcome definitely is negative. If the mean is positive, the outcome. But using our model, a complementary alternative, it doesn't care whether your mean or your data, the center is negative, is negative or positive. So we try to compare the efficiency. How efficient? We use what is called relative efficiency. So the Siberian, the statistical mirroring, which the first one we use here, we call it a statistical absolute meaning mirroring. This absolute mean mirroring is very efficient, comparable to standard deviation by having 1.08. So if it is greater than 1, it means our estimator is not good. If it is below 1, our estimator is good. So this means they are very closely related, very similar in terms of efficiency. We compare the coefficient of variation and with its complementary alternative. We just name it rho minic mirroring, which have 1.00. It means they have equal efficiency. This is the resilience outlier. I know this plot, maybe if you want to know more about these pictures, but let's go straight to the conclusion. The statistical absolute minic mirroring, this is the we try to compute the percentage level of resistance when we maintain 50% relative error. So when you look at the standard deviation, it can only resist our absolute statistical minic mirroring can resist 7.9% error. Even if the outlier, that means if you can contaminate your data point by 7.9% of it, the value will not change, will not give you a relative bias above 5%. So similar with standard deviation, which is 1.5. It means our proposed estimator is 5 times more resilient outlier than the conventional statistics. Similar with coefficient of variation, comparable to statistical rho minic mirroring, which is 1.5 times more resilient to coefficient of variation. So this indicates how resilient is this framework. I have returned back that table. So let's look at it. Some, which is statistical absolute minic mirroring, has succeeded. You see, independent of the transformation, you have the data, the outcome remain consistently the same. So this makes statistical mirroring a resilient, suitable alternative in making comparison of the data, irrespective, regardless of any linear transformation you have. Okay, let's see. We always represent our data using mean plus or minus standard deviation, isn't it, in research? But the interpretation of what that means, what that standard deviation means, is where we have a problem. Let me ask a question. If I have mean 1 million standard deviation and having mean standard deviation of 0.1, which one has higher standard deviation? I think the 1 million. So what if the mean standard deviation of 1 million is far greater than having having less than 0.1 standard deviation? No doubt. It's far. But what if having standard deviation of 1 million if the mean is, let's say, 1 trillion? But in this case, we say 0.1 is very small. What if the mean is just, let's say, 10 or 1? So you interpret standard deviation relative to the mean. You have to look at the size of the mean. It is based on the size of the mean you now conclude. So if you have many data, multiple data sets having different mean, so it's very difficult for you to compare their estimation. But using this absolute mean statistical minic mirroring, you don't have to worry. It doesn't care what is the mean. It doesn't care what is the size of your mean. It doesn't care whether the data is shifted, what transformation, what location shift you have with your data. So this qualifies it to be a winning, to win the expectation of having scale-ups invariance. And I'm very sure there is no any clear rule you can use coefficient of variation or standard deviation to say these data sets are the same. You relate to the mean, so it will fail. If you relate to the standard, it will fail. But this one succeeds. Okay, what is the drawback? Even though it's a problem, it has some drawbacks. We have to do justice to our. So one of the drawbacks, if your pattern of your data is very important, you shouldn't use it because it is permutation invariant. When you change the order of your data, but in most statistical statistics analysis, we don't care the position of your data. During measurement, which data comes first, which comes second, we don't care. Except that is the size or the pattern or the order is very important. That is the case, don't use statistical error. Then, it is when you are trying to make one comparison, you have to make sure that the pairing is there is a benchmark reference for the pairing. I'll show you what pairing means. And the two possible covariant by coefficient, you may have two coefficients that are not the same, but true translation will give you the same outcome. I'll show you how these limitations, how you can solve it, and it has no location shift. So if your intention of your analysis is just to neglect any location shift only, nothing, so don't use statistical, go to standard deviation. But for generalization or opportunity of comparison, you can still use statistical mirroring, and it will give you a reliable, valid. So here is the framework of this statistical mirroring. This is what we call covariance-based isomorphic optimal. This is based on a statistical framework. It has been proven to be bijective. When we say a bijective mapping or something is bijective, is there is one-to-one correspondence and having one-to-one, it has to be one-to-one and onto. A has to work with B1. A2 have to work with B2 in that manner. In a mirror, see, it's looking like what? A mirror. A reflection. There is a reflection. So this aspiration comes from the concept of isomorphism. Isomorphism, this is what isomorphism is. But we try to modify the concept of isomorphism by introducing a center. We have delta there at the center. So in this concept, I name this as isoreflective pair. So when you have a variable A and B, you pair it to introduce another element, which is the center, delta. That concatenation of these two variables is what I have named as isoreflective pair. Reflection, remember reflection. Iso, that is, they are one-to-one, reflecting around a center. Then I introduce another domain, which is the R, which remarks all the elements of the isoreflective pair. So this is the concept of evidence-based analysis. Then, now this concept, we don't want to go deep into the mathematics. You can prove it that yes, A and B1 are one-to-one and projected to prove that this is isomorphism and satisfy the condition of bijection. So we don't want to go into the detail as it's a long this thing. Let's go. Okay. Let's go to the steps. These are the key steps. One, you have to make sure that you introduce a compulsory theoretical ordering. We introduce a concept of centering. We introduce a concept of what we call statistical mirror. That's how we name it mirroring. So that concept of statistical mirror design also have to make sure that our pairing of the isoreflective pair is efficient. We also try to deal with the center, which is the central normalization, and we now finally we have optoanalytic construction. I'll show you. Then this is the first stage, pre-processing. This pre-processing qualifies that is just it. But the second step, which is of analytic model calculation, is upon the use of covariant coefficient of proximity, the probability of proximity and deviation, and other alternative coefficients within this model. Okay, let's go to this. This is very interesting notations. I know it. So you see here. Let me explain. This is your data. Here, this is your data. Now, if covariant-based isomorphic analysis, you need to have two variables. Here we have one variable. So how do we transmute to create another variable? That is why the concept of designing a statistical mirror. That statistical mirror will now serve as another pair. T is your data. Phi is the mirror. So you have phi as your data. So phi is now be the mirror. So we conceive it to be the mirror if you use a mean. So if you assume your mirror to design your mirror using a mean, so you generate a number, equal number, a uniform number equal to the length of your data. If your data point, let's say, have 5, 1, 2, 3, 4, 5, if your mean is 3, then you say you have 3, 3, 3, 3, up to the length. So now you have two variables. So we transmute a univariate data into bivariate data to satisfy the condition of covariant-based isomorphic analysis. Now, if this is your data, so it means P is the center. So if you assume, if you follow this, you follow the formula, you have this Y rule of covariant isomorphic optionality. When you calculate, you have KC1, or you may have KC2. When you translate KC1 to KC2, you have the same estimate. In this case, you may have different, but when you take it as you translate it, you have the same estimate. And this estimate, whether the carrying X to P or P to X, it doesn't care about the rotation. It doesn't care. So the rotation here is BTS will give you KC1. If BTS will give you KC2. When you translate outcome, regardless of the rotation and the similarity regardless of the rotation of your data. Whether X is the left, the other one is the right, or you shift, or you vice versa. Now, having this framework, there are different types of statistical mirroring you can do. Based on this, just look at this one. If our phi is regarded as EX here, we have statistical rho, we have statistical absolute, we have statistical integral, X mirroring. Now, if statistical rho, what do you mean by statistical rho? Is when you just take your raw data. You doesn't transform your data. Maybe I have one data, but you just put it as an input. In case of absolute, you have to center your data. Centering the data, you subtract each data point from the center. If let's say the mean, so you subtract every data point from the mean. So now you have centered your data. So if you allow the model, you tell the model, hey, center this data. So you have to choose our option. That statistics we are doing is what we call absolute statistics. If you center it without returning the absolute value, if I center a data, because it dispersed around the mean, I have negative, positive and negative numbers. If I transform it into absolute value, I will remove the negative sign. They all be positive or they all be negative. So this is what is called absolute. So if you leave it like that, you center it, you don't make it an absolute, that is what is called integral. So if your mean, let's say I have used mean, so it will not be statistical rho mirroring. If I use meaning, it will not be mean. So now I have statistical rho meaning mirroring. So mimic mirroring is when your mirror is regarded as a mean. Or you can have statistical row medianic mirroring, or modalic mirroring, or multimalic, or minimalic. So depend on what you choose to be your mirror. In this absolute, you are not saying, now you say, no, don't choose the raw data. Center it. When you center it, you return the absolute value. You are toward absolute statistical mirroring. So if the mean of that is mean, you say statistical absolute mirroring, same way. In this integral, say don't return the absolute value, toward. So that make what statistical mirroring a very complex framework. Depend on what you want to do. What types of analysis? What do you want to silence from the data, and what do you want it to contribute in the variability of your data? So I may decide to say, okay, this is my data. I want scaling to contribute to the variability. So you have to use row. Or you have to find the suitable combination of parameters for you. This make it but very dynamic estimator. So this is just a optionalities. These are the formulas. We can't explain. We don't have time to explain all these details of this formula. This is automorphic optionalities. Another one is isomorphic optionalities. Our concern is that isomorphic. We don't have this automorphic optionalities. Okay, this is the implementation. We have implemented this because you are the end user. You don't have to stress yourself going through all the details of formula, whatever. So we try to implement it using Python. We implemented the code. If you are good in Python, you can trick with codes. You can visit this website to download the code. Or if you want to use a Python interface, you can install it in your Python as a Python library. You can download it direct from PyFile. Or you can just command pip install. It will install it in your Python using this command, as I have just stated. Pip install KBO models. So this statistical, there are so many packages, so many modules within KBO models, but if you install it, statistical mirroring is there within this package. We decided to make a computer application, a software application. If you are not good in Python, using this graph programming language, you can use just free software, put your data, run it, and get your data. You can download the programs using this link. You download it. So this is how you can download the code. It's deposited in this Mendeley data. Visit the website. That link, it opens you there. You click on download the code. If you want to go to the PyFile index, you want to have the modules. This is the interface. This is how it will look. You download it here. Click on here. It will download the package. You can install on your Python manually, or you can just use pip install command directly without just coming in. It will download it and install. Or if you click on computer application, it will show you here. It has deposited in the Mendeley data. You come here, you download. You click on here, download the zip folder. Within the zip folder, you have the data. So I will show you. I will run through this application. You see how you can use. Very user friendly. So let's go. Can we go to the takeaway, or we should run the softwares so that you see how applicable they are. Okay. Prof, please, we need your assistance. We need to switch. Okay. Can we proceed before? Okay, let's proceed. Here are the key takeaways from the presentation. How many takeaways? 4. So you all have 4 takeaways to go with. 1, statistical mirroring is crucial in summarizing, inferring, and predicting, and in comparing data. That is statistical estimators. There's this classical dispersion measures. They face challenges regard to robustness, efficiency, and interpretation, and even the scaling invariance limitation. Then, the introduction of this statistical mirroring provides you with a resilient, efficient, and transformation invariant alternative to traditional dispersion measures, and proper estimation selections depend on the specific task, depend on the characteristics of your data, the goal, the purpose of your analysis, and the limitation of the estimator. So most scientists in biological sciences, we fail to appreciate the limitations of this estimator. There is one rule. You have your data. It's your data that will find a suitable statistics, or it is the statistics that look for the data. You have to know. You have to keep in your mind, it is the data you have that will find a suitable estimator. Not just that I have data, I see my friend publish a paper, he used t-test, just run through t-test, whatever result is given, you just conclude. So you end up having erroneous conclusion and bias. Produce some bias or having a wrong conclusion. Okay. Advancing botanical analysis with very innovative and adaptive statistical mirroring technology, methodology, and statistical mirroring bridge the gap that has existed in scientific literature by making data driving more precise and more interpretive. And if you're interested in using this, is welcome. You can study it, see how you can modify it, to come up with your new model, your new methodology. There are open opportunities there. So, especially the Caribbean based optimization. Anyway, I hope so. It's really interesting. If you understand how the framework works, I'm very sure you might have your own methodology. And these are some of the selected references. And thank you for listening. Finally, if there is time, I can switch to the application. We just run one of them to see how interesting the interface. I need someone to switch. Someone has to help us. A run code. Just one. A run code. Okay. Go to the folder. Are we sharing? Do you want to share it or just you would like to share it online? Can you share? Okay. Share. Okay, let's share and write the folder. Look for the folder. Okay. So, this one. Click on this folder. Okay. Click on that one. So click on the first one. Yeah, that one. So thank you. So once you click on it, for the application it opens to this one. Is it okay? It's just displaying here. It displays here, but not on the screen. Okay. Share screen. We need someone who will. You know what you use? Okay, wait.
Okay, stop sharing. Share only this. Just stop sharing. Okay,
Share.
where is it? Can you go?
Let's see what is it. Okay. Amazing. So this is the let me try to maximize. Okay. So this is the interface. Here you just put your data. You can copy it from the Excel or from the table. You just paste here. Here. If you are typing it manually, you separate by comma. Let's say I have a data, a random data like this. You put it. Then you now ask yourself, what do you choose to be your mirror? Is it the mean? There is option here. You can use median, mode, or any reference. So let's take a mean. Then you ask yourself, how do you tell the model to center your data? You want it to center it from the mean, mark minus mean, and return absolute value. So there are so many functions here. There are so many options to select. This one, it's centered by mean and return absolute value. This one, it's centered by median and return absolute value, by maximum, by minimum. The same way it goes like this. There are so many options you can choose. It can return it negative, or you can even decide never, so that it will not center your data. So let's work with the mean. Let's work with this one, center by mean and return absolute value. Then you ask yourself, how do you want it to sort the ordering? It has to, because it is permutation invariance, it has to neglect the order or the pattern of your data. So do you want it to sort it in ascending or descending? So let's go with ascending. Now, how do you want the pairing? Because you have your data, you want to establish isoreflective pair, the mapping. So do you want it to be head by head or tail to tail? A head to head is the first item of your value, the first element of your data, are maximally distant from the center. This is head to head like this. If this is the first element, this is the first element for this. If I pair it like this, that is the first is maximally distant to the center. If I do like this, this is tail to tail. That is the first element and minimally distant to the center. So you have to ask yourself, how do you want it? But in case of this statistical mirroring, we maintain a head-to-head pairing for comparison and reproducibility. Then you ask yourself, what result do you need? There are so many functions here. Do you need the Kiberian coefficient of proximity? If yes, fine. You click on it. You select compute. It gives you the result. You can copy it. You can copy the result. Or paste it anywhere you like. Oh, I'm not interested in this. I'm interested in the probability of proximity. How closer are the data points to the mean? You click on this, it gives you the result. This is in probability. You can multiply by 100 to turn it to percentage if you want to work with percentage. Am I looking for the probability of deviation? Yes. You click on it, it gives you the result in probability form. Am I looking for all? If I'm looking for all the estimates, you click on this, you click compute, it gives you the result. All. You select which one. I think in the next version of this model, I will release it soon. I will try to make sure that as it is printing the outcome, it tells you which statistics do you use. I think if you can follow the next version, we'll try to improve the display of the outcome. It will order it in a list-wise manner, not in this way. So I will soon shall publish the next version. So this is how it works. Okay, let's go to the next one. Please, can you help us? To the switch to the next one, because this is the final. This one is when you are working with just only one data. So you have many data in an Excel sheet. You have it in an Excel sheet. You save it as a CSV file or in Excel. So how do you use this statistical model? We go to the font. Yes. Select the second one. The second one. Okay, before you go.
Is it?
Yes.
Okay, let me just stop. Where is it? This one.
Yeah, that's not.
Where is that?
Another 30 minutes. This one. Second. The second one. To pop up. Let's let it open.
I have to stop sharing and share this one.
Okay, let it open first.
Still level.
It will load. Okay. Thank you. Thank you very much. Okay, you can maximize. So this is the second application. Here, you just need to import your data. You click on this. It will direct you to your document. If you have any data, you select a folder, any file, you save your data, you upload. Any data, we should have generated a data that we can just test. Let me cancel. So when you upload it, the same way you select the mirror, you select this one, you click on it. So I don't know time. Can we? Yeah. Yeah. Can we generate a data? Okay. Yeah. I should minimize, no? Minimize. Okay. Right. I just need to go to the desktop. Desktop. Okay, does you want to Excel? Thank you for
Any Excel
worksheet. Excel. Let's create so much. Save and let's go. Let's distant your data point are to the mean, not only mean to the median. Let me summarize, let me generalize to a center.